Yeah, the physics community has taken a great stabbing to the heart because revolutionary physicist François Englert passed away this week. He was one of my favorite physicists because he really combined teaching physics and doing research in it. Because there are physicists like Michio Kaku who are actively doing research in physics like string theory and will do research in physics until they die. But there are also physicists like Neil deGrasse Tyson who leave physics and tend towards science communication. But Francis Englert was one of a kind, an exceptional physicist who did huge research in it and also inspired the youth to learn physics, and he also taught physics how to understand it with his many journals and books. His work heavily relied on quantum mechanics, but he is most famous for being an architect in the Standard Model. He, along with Peter Higgs, yes, that Higgs boson, created the boson particle or formulated how massless particles gain their mass through the boson field or Higgs field. Now, in his memory, I'm gonna just teach y'all or give you the gist of quantum mechanics as his work heavily relied on it. As of now, I'm not proficient enough to do anything about his work because that is too complicated. So quantum mechanics. Quantum mechanics is a probabilistic. I'm gonna just leave off my glasses now. Quantum mechanics is a probabilistic nature of how reality works, and somehow it is our best framework to deal with. In Newtonian standard case, if we have the time and position, the particle has a position and the time travel from the origin, we can figure out everything about this particle. Its momentum, force, curl, everything can be measured out from these two frames, the position and time. But in quantum mechanics, when we are dealing with microscopic particles, things are kind of different. We're dealing with probabilities and probability theory throughout. So every particle has a quantum state. We denote that quantum state by this bracket, but that's for later. It's a quantum system has a wave function which inherits this quality. So if this is a wave function, one can clearly see a particle has the greatest chances of being at here, a lesser chance of being at here, and no chance of being here. Let's denote this point as C. Let's just measure the wave function, which is denoted by psi, and the probability density is given by the modulus square of the wave function, but that's for later also. So if we measure the particle at C, we say the wave function collapses and we give a spike. We have a spike on that point because that is where the particle is. And quantum mechanics really is this. This is the basic framework of quantum mechanics, and this system divides, the quantum mechanics framework divides into three perspectives when you ask one simple question. And that question is, where was the particle before being measured at C? Now, there are three positions. First, the realist position is that the particle was always at C. Famously, Einstein was a great advocate for this realist position, but I'm going to explain why that is false. This position contradicts the laws of physics, because if we measure the particle at C, so at this point the momentum was C, or sorry, the momentum was 0, but measuring at C, we say the particle was always at C. So the position of the particle was always 0. So we know the position and momentum at the same time. No, there can be Heisenberg's uncertainty principle. You cannot simultaneously measure the position and the momentum of a particle. So the realist position gets out of the way. Then we have the orthodox position. This was the Copenhagen interpretation that was formalized by Niels Bohr and Heisenberg. This is the best framework. This framework says that before being measured at C, the particle was at a superposition over the wave function. And that's that. When we measure the particle at C, the wave function collapses and the superposition collapses. So we have just one point. That is the highly regarded as the best approach in dealing with quantum mechanics. Then there is the agnostic approach that says that this question is nonsensical to ask, because to know anything about this particle is to make a measurement. So you cannot ask what the particle was before taking a measurement. That's it. But curiosity is the vein of humankind. You cannot refrain from asking questions. So that is out of the part two. Then there is another approach, but that is more of an interpretation. The main interpretation are the Copenhagen interpretation and the many worlds interpretation. Now the last one is kind of funky because I don't even know physicist alive really understands what the many worlds interpretation says. Some physicists have tried, but really didn't get far. It just says that when we measure something, every superposition stays. It's just the reality breaks into two branches. It's like some sci-fi thing. No, we wouldn't get into that. Now comes how to learn quantum mechanics or how to learn physics in the first place. And my advice to you would be the same advice that François Englert gave in his journals. That just to stare at it. That's it. Just stare at the thing you have. I remember learning that or just reading in that journal and then plugging in the computer and just stare at quantum mechanics, and hours and hours would go by. I would understand a thing, but somehow it just clicked in the brain. Then I can just practice and do anything like things like this. I remember one time I was staring at an equation for 3 hours. It was 4 a.m. in the morning, and somehow it just clicked. And that's when I realized that staring at it is the secret. Things like the Laplacian or the Schrodinger equation, which goes like this: h squared 2m. This is the Schrodinger equation of a hydrogen particle in spherical coordinates. It would be 1 over r squared del over r. This is the Schrodinger equation in a spherical coordinates. When this framework you would need to solve the hydrogen atom for Schrodinger equation. Now, I stared at this equation for like 4 hours. They didn't click anything. Then somehow it just did, and that's the secret. You need to just stare at it. Stare at electromagnetism. You wouldn't understand shit about electromagnetism. DL. Even grad student won't understand anything about electromagnetism. But the secret that François Englert always proposed, just stare at it and it'll click one time, then it'll click 2 times, then you will practice it and it'll be ingrained in your head. So in loving memory of François Englert, that's it. That's quantum mechanics, and that's the secret to learning science. Just stare at it for hours and let it click itself.